Welcome to the flock. Let's dive into some calculations of melting, then heating, then completely boiling away a chemical substance. Stick around to see how a calculation just like that one is done. Not only do intermolecular forces cause each different chemical to have a different deltaH fuse or deltaH Hvap, which are your enthalpies of fusion or enthalpies of vaporization respectively, but IMFs also determine this heat capacity of a specific substance. If a substance has stronger intermolecular forces, it's harder to break apart that chemical from itself. In other words, it takes more energy to change from a liquid to a gas or from a solid to a liquid. Its heat capacity is larger. It requires more heat to get it to do a phase change. Whereas if a substance has weaker IMFs, it takes less energy for that substance to go from a liquid to a gas comparatively. This heat capacity that I mentioned, which is caused by the IMFs, is represented by the letter C. It's also referred to as specific heat, and it's different for every single chemical and state out there. So not only is it going to be different for water, for example, but water's liquid state and solid state also have different specific heat capacities. But the C, or heat capacity value, that you should have memorized for water is 4.184 joules per grams times degrees Celsius, which can also be written like this, if this way of units makes more sense to you. We're going to use this C, or specific heat for specific chemicals, in our heating equation. Our energy of heating equation is represented by a Q for energy, the C for specific heat, G for grams, or M for mass in grams, and delta, which always means change in, degrees Celsius. That's your temperature value you're going to use. Remember, the units for C were joules divided by grams times degrees Celsius. That's why we need our mass to be in grams and our temperature to be in degrees Celsius, so that they'll cancel with the denominator. Also remember that if the question is asking about water, we can use that 4.184 value. However, if it's asking about a different substance, you need to look up the specific heat value, or the C, for that substance, in addition to looking up that substance's individual deltaH fusion and deltaH vaporization values. Let's go ahead and try just applying this energy of heating equation to the following question. How much energy, Q, does it take to heat 355 grams, or 12 ounces, roughly, of water from 0 to 50 degrees Celsius? We know that the change in temperature is going to be our final minus the initial. So that would be 50 degrees Celsius minus 0, which is just 50. We know that this question is referring to liquid water, and so we're going to use the specific heat of 4.184 joules divided by grams times degrees Celsius. And our mass, of course, was given to us in the question, so 355 grams is the mass we're going to use. So all we have to do is plug and chug. We've got Q is equal to 4.184 joules divided by grams times degrees Celsius, multiplied by 355 grams, also multiplied by our 50 degrees Celsius. Now we can see that the joules cancel here, the degrees Celsius cancels here, and our final energy will be in units of joules. When we multiply those three values together, we get 74,266 joules. We could also convert this to kilojoules by moving the decimal over 3 places and rounding. So that would be about 74.3 kilojoules. Now that you've seen me try it, go ahead and pause the video here and see if you can solve the energy Q for the following question. Ready? Go! Let's check your answer, see if you got it right. Hopefully that's the answer you got. And if you did, pat yourself on the back. Let's move on. Questions like this are the ones that usually trip up chemistry students, because not only are we heating, but we also have to use deltaH fusion first to melt. Then we also have to go up on the diagonal on a phase change chart. If you're unsure of what I'm referencing to there, make sure that you check out my video linked in the description below about how to read phase change charts. So not only do we have to read on that diagonal of heating up, that's where the Q equation is applied, but then we also have to boil away using the deltaH or enthalpy of vaporization to do so. So there are 3 separate calculations we'd have to do to successfully calculate a question such as how much energy does it take to melt 10 grams of ice, then boil it away. The first step is to tackle that melting aspect. We know that melting is going from a solid to a liquid, so that's where we have to use the deltaH or enthalpy of fusion. Let's apply it to our magical line to freedom. We're going to start with our 10 grams of given mass of solid water, H2O(S) for solid. We know the molar mass of water is roughly 18 grams per mole because there's 1 oxygen and 2 hydrogens, so that's 16 plus 2 gives us 18. And we know that the deltaH fusion value for water, it's frozen water, i.e. solid ice. We know that value to be 6.02 kilojoules per mole. And that's what we're going to plug in here since we're after the energy. And of course, energy is in units of joules or kilojoules. So let's put that on top per 1 mole of water. Then we can see that grams cancel, moles of water cancel, and we are left with units of energy, so we know we're on the right path. And when we multiply 10 by 1 by 6.02 divided by 18 times 1, we end up with a value of 3.34 kilojoules. Now we need to apply the heating part. So if you're thinking back to our phase change, we just went through the melting part, and now we need to get through the heating part. Anytime we're going to be heating something, we should think about Q equals C times mass times delta T. In this case, we have water still, it's ice, so we're going to use C as 4.184 joules divided by grams times degrees Celsius, and our mass is 10 grams, is heating water entirely from its 0 degrees Celsius to 100 degrees Celsius to boil it. So we would take 100 degrees Celsius minus 0 degrees Celsius where water freezes, and we would end up with 100 degrees Celsius as our change in temperature. We see that our grams cancel, our degrees Celsius cancels, and all we have to do now is multiply 4.184 by 10 by 100. That gives us 4,184 joules. Now this is where we need to be really careful. Warning, warning. This is where we need to be very careful. Our units need to match. Before we calculated in kilojoules for that melting step. Here we have units of joules. So make sure that you convert this to kilojoules so that all of your units will match in the end. And because of that, we're just going to move this decimal back 3 spaces so that we can convert it to 4.184 kilojoules. And now the last step is boiling away the water. We've melted it, we've heated it all the way up to 100 degrees Celsius, and now we want to boil it all away. Well, we still have 10 grams of water. It's in a different state, but there's still 10 grams of it. So that's what we're going to start with. And we know that we're going to need to get rid of the grams. We're going to use our molar mass, same as it was before. Except now, since we're dealing with boiling away, we're going to use our deltaH vaporization value for water, which is also something you should have kind of on the top of your head as 40.6 kilojoules per mole. That's what we're going to use as our conversion factor here. 40.6 kilojoules per mole will get us units of kilojoules, which is the energy we are calculating for. Our units cancel, grams cancel, moles cancel. We are left with kilojoules. And when we multiply the 10 by 1 by 40.6 and divide that all by 18 times 1, we end up with 22.3 kilojoules. Of course, now the last step is just to add up those last 3 steps together. From the melting part, we had 3.34 kilojoules. From the heating part, we had 4.184 kilojoules. And now from the boiling away part, we had 22.3 kilojoules. So our final answer is 29.824 kilojoules. In other words, it would take 29.824 kilojoules to melt, heat, and completely boil away 10 grams of water. Now that you've seen me give you an example of applying this 3-part calculation, Go ahead and pause the video here and see if you can solve how much energy it takes to melt 15.46 grams of ice and then boil it away completely. Let's check your answer and see if you got it right. So hopefully you got a final answer of 46.51 kilojoules. Remember that in step 1 you're melting, so you have to use your deltaH of fusion conversion factor. And when you're heating, you're going to always use this Q equation. And then to boil away water, you're going to have to use your deltaH vaporization conversion factor here in 3 separate steps. Whew, that's a lot of work for one question. Chickadee check yourself before you wreck yourself. Make sure that you can test yourself and answer these 2 calculations before moving on to the next chemical concept in the DeConta series. If you'd like to check your answer, please post your answer in the comments below and I'll be happy to let you know. In this lesson, we went over how intermolecular forces cause different chemical substances to have different specific heats or heat capacities, not only for the different chemical substances, but also for the same chemicals' different states, going from a solid to a liquid or a gas. We were then able to use the specific heat capacity for a chemical, C, in the heating equation, which is Q, energy, is equal to C, specific heat, times mass in grams, times the change in temperature in degrees Celsius. We could then apply the heating equation in tandem with deltaH fusion and deltaH vaporization for a full, complete phase change diagram, melting, heating, and then boiling away entirely. Please give this video a quacks up, and when you're out of luck in chemistry, subscribe to the duck. Quack you later.
No ducks, no glory.